have we proved this fact? Please look at the whiteboard. That composition is associative. P composition Q composition R equals P composition Q composition R. Have we proved it? Probably before given that example. What do you think?
Yes, I think.
Okay. And what about the converse of composition? What do we take the converse relation to this composition? What is it?
Q inverse composition P inverse.
Exactly. Okay. By the way, what does it mean? What is the converse of P? What is it? What is this relation means? Of which pairs does it consist?
BA, provided that AB.
Exactly. We may take all such pairs BA, where the first coordinate comes from the range of P. The second one comes from the domain of P, and it is required that AB belongs to P. And what does this composition mean? When two elements, 2 points are connected by such an arrow, when such a pair X, Y, belong, when does it belong to the composition of P and Q? What does it mean? That means that there exists some intermediate point such that there is an arrow XZ and ZY. By the way, do you remember all this stuff about arrows, pairs?
Yes.
What is it? It is a set of all such pairs where points are connected by a path of 2 arrows. The first arrow from P and the second one from Q. Something like transport accessibility with a change. So you can reach Y from X, first traveling by, say, plane, then by train, with a change at some station Z. So formally it is a set of all pairs XY, where X comes from the domain of P and Y comes from the range of Q, such that there exists some intermediate point Z with X, P, Z and Z, Q, Y. Do you agree?
Yes.
Okay. And by the way, what does it mean? The domain of a binary relation, what is it? What is the domain?
The first element coordinate.
The set of all first coordinates. So if R is a binary relation between some sets A and B, the domain is a set of all such elements from A for which there exist some counterparts, such that the pair X, Y belongs to R. And likewise, what is the range? The range of R is a set of all the second coordinates of our pairs, all such Y's which are second coordinates. That is, for whom there exists there exists a counterpart x such that x, r, y, x, y belongs to r. So graphically, if a binary relation is depicted as a diagram, say we have pairs 1, 2, 2, 2, say 2, 3, and 4, 5. If we have just such pairs, what is the domain of this relation? What is the domain? And what is the range? Please name all the elements of the domain.
1, 2, 3.
1, 2, 3. Really? Why,
4, 4.
why
1,
1
2.
belongs to the domain? Because there exists an arrow which starts at 1. It goes to 2 from 1. So 1 is the first coordinate, yeah, of some pair. So 1 belongs to the domain. What else?
2.
2.
2 belongs to the domain. In fact, we have 2 pairs that for which 2 is the first coordinate. 2, 2, and 2, 3. What else?
4.
4. Exactly. And these are all points from the domain. Not about the range. The range is a set of the second coordinates. What is it?
2, 3.
2
1.
and 3, because there are incoming arrows that end at respectively 2 and 3. What else?
5.
5, of course. Is it clear? Is it clear?
Yes.
But sometimes we are interested in restricting this domain somehow or range. We are interested in all such points which are reachable from somewhere, from some set. So assume that we want to take some specific set. Say, assume that we have another point, say 6, 7, or whatever. Let us consider this set x. Let x consist of exactly 2, 5, and 6. Assume that we are interested in all such points which are reachable from at least one point from x. This is known as the image. The image of x, so the image of x under R, or for short it may be called the R image of x. What is it? Informally, it is the set of all points which are accessible, that is via one arrow, from a point in X. So what is it? What do you think? What is it? Let us give a formal definition. This is the symbol for image, R and X in square brackets. Sometimes they use round brackets, but I don't like this practice. What is the range? How can we define it? After all, it is given that our R, by definition, we have just binary relations between some prefixed sets. So R is a binary relation between A and B. What is the image of X under R? All the points which are reachable from X. After all, can you name such points with this informal definition? I mean, have you understood it? Which points are reachable from X?
3, for example.
3. 3 is reachable because there is an arrow that starts from somewhere in X but leads us to 3. What else?
2.
2 also.
2. 2 is also reachable. What else? Is something reachable
That's all.
from 6? No. From 5? No. This reachability thing refers to the existence of one arrow path, strictly one arrow, no more, no less. So these are just all such points where an arrow leads, an R arrow leads from somewhere in X. Is it clear?
Yes.
We can easily define it formally. Look, it is a set of all such points y, where from. You can take that it is a point from B, or simply you may say that it is a point from the range of B, such that there is an arrow from R that ends at this point, but it is not all you need. Not all you need. Besides that, you want to say that X belongs to this capital X. Excuse me, range not of B, of course, but of R. Is it clear? Oh, but let us rename Y to B and X to A. Is this idea clear?
Yes.
What is the difference with the range? What is the difference with the range? The main difference lies here. So it is something like a relative range, restricted range. After all, it is clearly a part of the range. Is this idea clear?
Yes.
But can you express the range in terms of the image? The range is the image of what?
The domain.
Of the domain. Exactly. It is the image of the domain, or you may say that it is the image of our set A. The range is a set of all second coordinates. But the image of X is a set of all second coordinates of pairs whose first coordinates belong to X. Is this idea clear?
Yes.
Is it clear?
Yes. Yes.
It is very simple. And what is the pre-image? Pre-image is basically pre-image is just the image under the converse relation. So you may say that the pre-image of X under R is just the image of X under the converse relation. But you can give a better definition, a little bit better definition. So formally, what is the pre-image? The pre-image is a set of all such points. Where from? From the range of what? We are doing all the same, but for the converse relation. From the range of what? Please continue. It is important to understand. The converse relation, yeah? Such that there exists what? Let us call it B, such that B R converse A and B belongs to X. Is it clear? It is just by this definition. Does everybody agree? But we can easily simplify it. We can easily prove that this equals something more neat. Ladies and gentlemen, what is the range of the converse relation?
It's the domain part.
Exactly. So there exists B such that B R converse A. This is equivalent to what?
To AB from R.
And B belongs to X. So what is it? What is you can take this thing as the definition. It is a set of all points where from some point of X is reachable. So informally you can say that this is a set of all such points where from a point in X are accessible. Is this idea clear? Is it clear? Okay, so now let us return to our example. We have already computed the image of X, but what is the pre-image of X? You know, the pre-image is the set of all points where from at least one point from X is accessible. Where from can you come to X?
From 1?
From 1, exactly. From 1 you can reach 2. What else? What about 2? Can you reach a point in X from 2?
Yes. 2.
Exactly. Why is this loop arrow? 2, 2, the pair 2, 2. What about 3? Can you reach a point in X from 3?
No.
No. There is no outcoming arrow from 3. Exactly. What else? Do we have any other arrow in this pre-image? Excuse me, any other point in this pre-image?
4.
4, exactly. From 4 you can reach 5. Anything else? No. So this is our pre-image. It is quite clear that the pre-image is indeed the image under the converse relation. Is it clear?
Yeah.
Any questions? Okay. Let us prove a few properties of images, and automatically they are properties of pre-images. as the preimage under R is just the same as the image under the converse relation. First of all, what do you think? What is the image of the empty set? What will it be? Where can you go from nowhere?
Empty set.
Exactly. And another important statement, what if you take the union of two sets? Which points can you reach? In fact, it is just the union of two images. These statements hold always. Let us prove them. It is easy. The first one. Okay. First of all, I am interested in the image of the empty set. What is it? Let us come back to the definition. It is a set of all such B's from the range of my relation such that there exists A and so on. Okay, look, what do we have? It is a set of all such points in the range of R such that for some A, we have A, R, B, and A belongs to which set? It is the image of what? Please be more active.
The empty set.
The empty set, exactly. Ha! But may this statement be anything except falsity? No, it is false. That's always false. So we have a conjunction whose one member is false. What can you say about this conjunction? It is always false, isn't it?
Yes.
So what do we have? We have the set of all such points from the range of R for which a false statement holds. May a false statement hold? Clearly not. So may we have any such point? No. The set is empty. Nothing can be its element. Is it clear?
Yes.
And now let us prove the second part. Assume that B belongs to this set. What does it mean? It is quite clear that means that there exists A, which belongs to this union, and where from B is accessible. Do you agree? This is just by definition.
Yes.
Is it clear? Do you have any doubts?
No, everything clear.
And now, with a few logical transformations, we shall make what we need from this statement. So what do we have? There exists A such that either A belongs to X or A belongs to Y. This is equivalent, clearly equivalent to the first statement, and A, R, B. Now, a little of logic. You know, alpha or beta and gamma. Assume that we have such a compound statement. Do you remember this stuff about compound statements, truth tables? Huh?
Yes.
This is everywhere in mathematics. So this statement is logically equivalent to what?
Alpha and beta.
Alpha and gamma, or beta and gamma. These are Greek letters. So What does it mean? That means that what we have here is equivalent to such a disjunction. Yeah, under the quantifier, there exists A such that A belongs to X and A are B, or A belongs to Y and A are B. Aha! And now we need another logical transformation. Assume that there exists something which satisfies either A or B. We have two predicates, A of X or B of X. So there exists a unicorn which is either white or tame. What is it equivalent to? What do we have?
There exists x such that p of x, or there exists x such a
Exactly. It is a law of logic. We cannot prove it formally, but we can explain it. In fact, we believe such things are like axioms. Okay. Assume that this is true. Then we have two cases. Either there exists X with property A, or there exists something with property B. In the first case, let us take this very X with the property A, and then for this X, A or B will hold. The same when X satisfies B. And vice versa. Assume that X satisfies this disjunction. Then we have still two possibilities, two options. Either X satisfies A or X satisfies B. In the first case, there is X which satisfies A. I hope it is quite clear, is it?
Yes.
Okay. So now we have this one or this one. It is formal, but it is very easy. Ha! But this thing says that there is an arrow from somewhere in X to B. That means that B belongs to the image of X. And likewise, here we have that B belongs to the image of Y. In any case, B belongs to the union of these two images. So B belongs to the image of the union if and only if it belongs to the union of images. Is it clear?
Yes.
As a corollary, let us prove that this operation that is taken an image or pre-image is monotonic. That is, whenever X is a subset of Y, then R of X is a subset of R of Y. Let us prove this thing. It is easy. Does anybody have any idea? This is given, so what should we do? We want to use this thing, our second statement here. We are going to use this statement. What should we do? We have to introduce somehow the union. Let us move it into our play. Isn't it obvious?
X Y intersection X is equal to X? Or
Intersection, no. Look, we have proved a thing about union. Why use intersection? This is equivalent to the fact that the union of X and Y equals what?
Y.
Exactly.
Why?
Okay, exactly. But clearly, equal sets behave identically. We should know it quite well. As equal sets behave identically, their images are identical. Do you agree? And according to our previous lemma, lemma 1, claim 2, this equals the union of R of X and R of Y. So we see that the union of these two sets equals one of them. Hence, R of X is a subset of R of Y. Is this idea clear?
Oh, yeah.
So, taking an image is another monotonic operation. For greater set, it generally results in a greater set. As an exercises, let me give you two exercises for your seminar class. First of all, you should consider what does it mean, what is R of the intersection. From corollary to it, it follows that this is included into both R of X and R of Y, because X intersection Y is included into X and it is included into Y. But another, the converse inclusion is not generally true. It is not generally true. And another exercise is about composition. It is interesting. What if we take an image under some composite relation? What is it? What is the image under composition? What do you think it be? So which points are reachable from X first by R and then by Q? What do you think? Which points are reachable first by R and then by Q? Do you have any idea? Which cities are reachable from your native city? First by train, then by plane. Exactly those which are reachable by plane from all the cities which are reachable by train from your native one. Is it clear?
Yes.
So the image under composition is just the image of the image. Look. You know this strange stuff with composition. It is defined the following way. First acts Q and then acts R. So this is a set of all pairs which are connected by a path where Q comes first and R comes second. And this fact explains it explains this strange convention you know, if you want to first apply Q and then apply R, you need such a way to write it. Is it clear?
Yes.
Okay. So far, we have developed a series of binary relations. We have all set theoretical operations available to work with them, like intersection, union, set difference, complement. We have two specific operations, conversion and composition. And besides that, we have images. And now let us apply this theory, this formalism, to define functions. What is a function? Intuitively, function is one of the most important notions of mathematics. So in mathematics, functions are very important. But before some point, functions were understood intuitively as some laws, some dependencies between magnitudes. So they were understood and treated intuitively. But at some point, this had proved inadequate. By the way, what is a function? Say something about that. If function is so important for mathematics, and I'm sure you have little doubt that functions are very important, functions are everywhere in mathematics, please try to define a function. What is a function?
Is a binary relation provided that for every
You are definitely cheating. So you are giving us a formalized set theoretic definition for functions. Of course, it is the right thing to do, of course. But if we pretend that we are more naive than we are, we might say that a function is a dependence of one quantity on another. Like in physics, say, I don't know. Do you know the second Newton's law from classical mechanics?
Yes.
Please state the law.
If the sum of forces in an object is zero, then the object is either moving with constant velocity or not moving.
I think that it is a particular case, but in general, the acceleration equals what? Of a material point, the acceleration equals the force applied multiplied by,
Over the mass?
of course. So something like that. So clearly we have a dependence. If you know the force applied, you can compute the acceleration. And if you know the acceleration, you can you can find the sum of all applied forces. Something like that. So in general, we need an abstract idea of a function. And our goal is to model functions, model such dependencies in purely set theoretical terms, using binary relations as a primitive concept. Okay, what will we do? We will introduce some special classes of binary relations. Okay. Some special classes of binary relations. Okay. A relation R is called functional, not yet a function, but functional. It is called functional. It is called functional, like a function, if and only if we have the following. For every x, for every y, for every z, if x are y and x are z, then y equals z. What does it mean in a diagram? That means that it is not possible, given any whatever x, it is not possible to reach two distinct points. If y and z are not equal, this is forbidden. Such situation is not possible. If you can access both y and z, they must be equal. Is it clear? And likewise, R is called injective. Have you had injections in your calculus course? Injective functions, injections.
Yes.
So R is called injective if and only if it is not necessary a function. This notion is independent of functionality. R is injective if and only if for whatever x, y, and z, if, look, y are x and z are x, then y equals z. So the same conclusion follows from the converse of these two. So what does it mean? That means that there are it is not possible to glue two distinct arrows together. Here we have no splittings and here we have no gluings. So if y is distinct from z, it is not possible that two arrows which begin from y and z respectively, that they has the same that they have the same ending point. Is it clear?
Yes.
What is the possible? What is the obvious relation between these two properties? R is functional when? If and only if
It's injected.
R is injective. Really? Is these two properties equivalent? Look, here we have x r y and here we have y r x. Think more. Please think more. If and only if the converse relation is injective. Likewise, R is injective if and only if the converse relation is functional. Is it clear?
Yes.
Let us prove it is very easy. What does it mean that R is functional? It is functional if and only if for all x, y, and z, if x are y and x are z, then y equals z. But we can easily transform this x r y into y r converse z. And here z r converse x. But this is exactly what we need to claim that R converse is injective. Is it clear?
Yes.
Two more properties. These properties will be a little bit more involved because they involve a parameter set. These are called totality and surjectivity. So we say that R is total. It is total for some set. Let's call it, say, H. It is total for a set H if and only if for every x from H there exists y such that x are y. What does it mean? That means that from every point in H, there is an arrow from R that starts at this point X. Is it clear? Clearly, that means that H is a subset of the domain of R. Is it clear? Huh?
Yes.
And likewise, R is called surjective. It is called surjective for a set H if and only if for every y from H there exists x such that x are y. So every point from H is an ending point for some arrow. Or equivalently, that means that H is a subset of what? Every point from H is an ending point.
Range point.
Exactly. Clearly, these two notions are also dual to each other. So we have the following lemma. R is total for H if and only if the converse relation is surjective for H. Likewise, it is surjective for H if and only if the converse is total for H. Is it clear?
Yes.
Okay, now let us consider a particular example. Assume that we have the following relation R: 0, 1, 0, 2, 1, 1, and say 3, 4. This is our R. Is it functional? Is it functional? Yes or no?
No.
Because we have still this one and
Why isn't it functional? Because here we have a splitting. We see that 0 R1 and 0 R2 But of course, 1 and 2 differ from each other. Is it clear? So it is not functional. Is it injective? Do we have two arrows, two distinct arrows that have the same ending?
Yes.
No, in fact, it is not the case. Look, we have two arrows, 0, 1, and 1, 1. But 0 doesn't equal 1. So we have two distinct arrows with the same ending point. Is it clear? So it is not injective. Is it total? Is it clear that R is not injective?
Yes.
But is it total? It depends on the choice of H. Of course, every binary relation is total for the empty set. In fact, it is total for every subset of its domain. Likewise, every binary relation is total for every is surjective for every subset of its range. But let us take something else. Let us take, say, the field of this relation, say 0, 1, 2, 3, 4. The set of all points, of all points which are either in the range or in the domain. Is it total for H? Is it the case that every point from H is a starting point?
No.
Why? Why isn't it the case?
Because we have 4. It's from edge, but it's
We
not
have
starting
4.
point.
4 doesn't belong to the domain. Hence, X may not be a subset of the domain. So similarly, it is not surjective for H. Why isn't it surjective? Let us take, say, 0. 0 is not, doesn't belong to the range, but it does belong to H. Is it clear? Hmm?
Yes.
Okay, let us consider something more. Consider this relation. Less relation for naturals. So you know, what is the diagram? 0 is less than 1, 1 is less than 2, 1 is less than 2, 2 is less than 3, and of course we have much more arrows from 0 to 2, from 1 to 3, from 0 to 3, and so on and so forth. Is it clear? It is infinite. But is it functional? Is it functional?
No.
Why?
0 less than 1, but also less than 2.
Exactly. But 1 doesn't equal 2. Is it injective?
No.
Please give a count example.
0 less than 1, 0 less than 2,
What
and 1
else is
less
less than 1? Less than 2, yeah. And 1 is less than 2. But of course, 0 and 1 are not equal. Is it total for what? Here we shall consider totality for n, for some prefixed set. So is it total for n? Is it true that every element from n is less than something?
Yes.
For every x, there exists y. For every x, I mean from the set of naturals, there exists y such that x is less than y. So that's true. Is it surjective? Is it surjective for n? Is it true that every y from n is greater than something?
No.
A count example, please.
0.
0. If we take 0 here, there is no element which is less than 0. Is it clear?
Yes.
Okay. Another example. Examples are very important. Another example is about our functions, our familiar functions. We know that every subset of the plane is a binary relation, let's call it, say, Q, a binary relation between R and R. In fact, every graph of a function is a binary relation. See, let us consider this graph a parable with the following, let's call it P. It is a set of all such points x and y, or all such pairs x, y, where x and y belong to R. So this pair belongs to R squared, where y is just the square of x. Is it clear? It is our parable.
Yes.
Please tell me, is it functional?
Yes.
Is it true that for each point, for each x, we have no more than one y? Of course it is. Of course it is. You know, every vertical line, every line parallel to the ordinates, intersects our set, our P at most 1 point. So it is indeed functional. Is it injective?
No.
Why?
Because we had two value of x had the same value of y.
Please give me an example such that something, okay,
1 and minus 1.
1 belongs to P, minus 1 belongs to P, but nevertheless 1 and minus 1 are distinct, so it is not injective. We have two arrows. We have two arrows, two distinct arrows with the same ending point. Is it clear? Is it total for R? What do you think? Is it true that for every x from R there exists y such that x py?
Yes.
This what should we take as y?
S square.
Exactly. So it appears that it is total, but is it surjective? Is it true that for every y from x, is it true that for every y from R, there exists x such that x py?
Yes.
Really? But what if I take -1?
Oh, no.
So in fact, it is not surjective for the set of all reals. Is it clear?
Yes.
We are almost ready. We are almost ready to define functions. But let us prove one more important lemma. This lemma states that composition preserves these classes. Composition preserves these classes. If P and Q are both functional, if they are both functional, their composition is functional. The composition of two functional relations is functional. If P and Q are injective, their composition is injective. A little bit trickier it is for totality and surjectivity, because you need you have to keep tracking of the set for which it is supposed to be total. So let us put it the following way. Assume that P is a binary relation between A and B, and Q is a binary relation between B and C, whatever. Then if so no, it is not that. Q and then P. If P is total for A and Q for B, and Q is total for A, then the composition is total for what? For which set? You know, the arrows go from A to C with an intermediate point in B. Is total for what? It is easy. Please think a little bit. For A, of course. And likewise, if P is surjective for what? For C, and Q is surjective for B, then the composition is surjective for C. Is it clear? Ladies and gentlemen, are you here? Are you present?
Yes. Clear.
So let us prove it. It's very easy to do. Okay. For functionality, I have that P and Q are both functional, and I'm interested in functionality of their composition. So what is given? What is given? It is given that P and Q are functional. And I need to prove that the composition is functional. So assume that there are some fixed points x, y, and z. It is given that x, y belongs to the composition, x, z belongs to the same composition, and what is required to prove functionality? What do we need for the composition to be functional?
Y
Please tell me, what do we need?
y equal to z.
Why? Exactly. Okay. It's very easy to do so. Okay. Look, xy belongs to this composition. That means that there exists some intermediate point, let us call it u, such that x, q, u, and u, p, y. Do you agree?
Yes.
Mm-hmm. And what do we have from here? There exists some intermediate point W such that X, Q, W and W, P, Z or Z. Okay. Let us group it together. So we have 2 points, U and V, such that X, Q, U and XQW and UPY and WPZ. Do you agree? Ha! But Q is functional. Q was functional, so what? We have 2 Q arrows beginning at X and going to U and W respectively. What does it mean?
U is equal to W.
Exactly. Ha! But if they are equal, they behave identically. So from these things, we have that there exists some U such that U, P, Y, and look, W is the same as U, and U, P is Z. Do you agree? But P is also functional. P is also functional. So, as a result, Y equals Z. And this is exactly what is required. Is it clear?
Yes.
Okay. And we may use our previous results. We may apply our previous results to prove that injectivity is also preserved by composition. It is very easy to do so. So for now, we know that functionality is preserved by compositions. Now let us prove that injectivity is preserved. It is possible to do it directly, but let us apply another approach. So what is given? It is given that P and Q are injective, and we are trying to prove that this composition is also injective. Easy. That is easy. First of all, First of all, when is a relation injective? We know from lemma 3, we know that a relation is injective if and only if its converse is functional. Do you remember this fact? Is it clear? So it is injective if and only if the converse of it is functional. Do you agree?
Yes.
Ha! But we know that the converse of something is, the converse of this composition is
Converse Q logic list.
it is the composition of these two converses. And we are interested in proving that it is functional. But in fact it is. In fact it is. By the same lemma 3, this is, it is enough. It is enough to prove that both these relations are functional. No, it is not by lemma 3. It is by our claim 1. It is by our claim 1. We have just proved. We have already proved that functionality is preserved. If two relations are functional, the composition is also functional. We know it already. So it is enough to prove that these two conversions are functional. Do you agree? But by lemma 3, it is equivalent to the fact that P and Q are injective. And they indeed are. Any questions? Is it clear?
Yes, yes.
What remains to be proved? Let us prove, say, that totality is preserved. We know that P is total for B and Q is total for A. Okay. And the fourth claim is similar. We won't prove it. So what do we have? We're interested in such compositions. We know that Q is a relation from A to B. Q is total for A. P is a relation from B to C. P is total for B. That is given. And it is required. It is required to prove that this composition is total for A. But what does it mean that it is total for A? By definition, that means that for every x from A, there exists some y such that xy belongs to this composition. Do you agree?
Yes.
Okay, let us prove this thing. Consider a point in X. Consider, a point X in A. Consider a point in A. What do we have? We know that Q is total for A. Q is total for A. Hence, there exists some U such that X, Q, U. Do you agree? But Q was a relation between A and B. So we may add that this U belongs to which set? It must belong to B. Is it clear? Is it clear? Do you have any questions? Ladies and gentlemen.
Yes, clear.
But P is total for B. That means that from every point from B, there comes an arrow. An arrow marked with P. So there exists U, there exists W, or let us call it Y, such that X, Q, U, and, U, P, Y. Ha! We see that there exists Y such that for some U, X, Q, U, and U, P, Y. So there is a two arrow path with a change at U, first by Y, then by first by P, then by Q, leading us to Y. So that means that this pair XY belongs to this composition. So this proves that the composition of P and Q is total. And the fourth claim, let us leave it as an exercise. You may either prove it directly or exploit the fact that a relation is total for some set if and only if the converse of it is surjective for this set, and vice versa. Is it clear? Do you have any questions? So far, we have proved that functionality, injectivity, totality, and surjectivity are preserved by composition. And on the other hand, conversion switches between totality and surjectivity, functionality and injectivity. And now we are ready to give one of our most important definitions, that of function. I will give this definition and we shall finish our lecture. So this definition is something we are going to consider next time mainly. But nevertheless, let me give this definition. A set F, look, it is very important. A set F is called a function from A to B. Please notice that there is no such thing as just a function, but a function from A to B. There are two parameters. We use the following symbol instead of these words. Look, F, column, A, arrow B. It is a statement that says that F is a function from A to B. So f is called a function from A to B if and only if the following three conditions hold. First of all, f is a binary relation between A and B. F is functional. And the last one, F is total for which set? For A. Is it clear? Practically, that means that every function is identified with its graph, with a binary relation. Is this idea clear? We shall analyze it in more detail next time. And now you are invited to ask your questions.